Okay, so anyways, this is the DTA information. Remember that if you have multiple forms of the of a like zinc here, zinc 2 plus, where only a portion of it will be in the zinc 2 plus form that's in solution, you have to then do an activity for that. So you bring that activity term out in front of your KF, like you did for the Y 4 minus, right? The gamma 4 minus for the DTA, okay? And again, the activity form is just the fraction that's going to be in that, right? And so that's going to be your 1.8 times 10 to the negative 5 here that we found in that previous problem. And then the 0.3 for this one. And then you would take your KF, which is that value right there. Multiply them together, that would give you a modified KF. This is a double prime KF, which would be the correct terminology for it. Though you can also, the correct terminology can be F, and then you put the species down here. That also works. Okay? I've seen both many times. A lot of people use the one with the species following it because this is difficult to do in a like Excel. Getting the subscript and superscripts, both. Okay, and so before your equivalence point, you're going to have 20 mils. Because your equivalence point is 50 mils, you'll do a fraction of the Zn remaining. And so that would be 30 out of 50, right? Remaining. So 30 out of 50 of the Zn2 plus remaining. Then you have to do your dilution factor. Everybody see that okay? Do I have to go through these each time, or are you guys good? No? Okay. Okay. So you get that concentration. Remember that nearly all the zinc is not going to be bound to the DTA. It's actually going to be bound to the NH3. So your concentration of free zinc is going to be as such. You have your free zinc here. That's going to be this fraction that's not bound times the concentration of your zinc 2 plus that you just figured out up here. And so essentially this is giving you the fraction of zinc that's not bound. This will give you the actual concentration of that zinc that's not bound, right? And so you get this number. Remember, you do all these things in P metal, and so you take the negative log of that. That gives you P metal. Any questions? Individually, the steps are actually quite straightforward and easy. The difficult part is understanding where you should go. And so don't forget to always evaluate when you're doing these problems. What am I doing? Where am I going? How do I get there? Okay? That's where people mess up. Is, you know, nobody's at this level is having problems with how to do a dilution, right? Nobody at this level has problems with how to do a negative log of a P of something, right? What people at this level have problems with is getting the whole thing. You know, assembling the steps, okay? And so you have to remember that, for example, what are you looking for when you're trying to figure out how much the PZN2 plus after addition of certain amounts of EDTA? Well, in this setup right here, you're looking at, well, your ammonia is going to be binding that zinc 2 plus, right? And EDTA will be binding the remaining stuff. So you're looking at what's remaining after that. And so you have to subtract off both of those first, right? Which is what we were doing up here. Okay. Okay. Okay, so at the equivalence point, what will we have? So remember that the equivalence point is where the concentration of the zinc and the EDTA in all of its forms will be equal, right? So the easiest way to handle the equivalence point is typically to figure out what this would be if it all bound and see what falls apart. Okay? All right, so at the equivalence point, your dilution factor would be 50 out of 100 because you need to use 50 milliliters to get a completely equivalent point to the equivalence point, right? Remember the 50 mils here. These are equal concentrations. So that means the 50 here for the EDTA would be equivalence point, right? Okay. So you take your wonderful dilution factor times your concentration of zinc, which you already have. That's what we were given. Or EDTA, whatever. Because you're assuming that's all formed the complex, right? So either number would work there. That will give you this number right here, 5 times 10 to the negative 4th. You go ahead and do an ice type problem where you take the formation complex, you put in your number from the dilution, right there, and then you see how much would fall apart according to that KF. Okay. You'll notice that because at A, we went ahead and before anything else, we figured out our KF double prime, right? We didn't actually need it for A, didn't we? You see, we never actually used it. That's always a good idea to get your constants worked out at the beginning of a problem, okay? Because then you have them if you need them. If you don't need them, at least you've already set up all your systems, right? This KF right here is found in a table. This right here is the pH 10 activity of EDTA, which we, again, could find in a table, or you could use the spreadsheet. Either one would work. Table is probably quicker unless you have the spreadsheet set up, which is actually, that's quicker. Then this one right here is actually what we figured out in a previous problem. So if you remember, we did a previous problem, just this previous one, where we looked at how much of the zinc 2 plus would be remaining from this amine right here, due to this amine, which binds it. You guys remember that from last time? Okay, so we figure that out because we have to have, that's the double prime, by the way, is the activity right here. Or the fraction, I should say, excuse me, not activity, fraction, right here. Which are those values? Okay, so we have this value at initial, we have 0 EDTA and 0 zinc 2 plus. We'll be assuming that the only source of that is our complex falling apart because we're at equivalence point. We're going to take that complex minus x, and then these make that amount, right? Everybody's good so far? We plug that into our typical KF expression. Again, we use our KF double prime that we just figured out in part A of this. Though you could have waited until part B, technically, because you didn't actually use it. And we plug in these terms here for those final concentrations, you know, the X terms that we normally get. In these cases, you can typically go ahead and assume that the X, you don't have to do the minus X here, and do the simplified version first, and then see what you get, okay? Remember, if it's a factor of 10,000 less than this number here, your assumption was good, right? Or if you have the formula set up that to do a quadratic, you can do the quadratic if you want. Either way is fine. By the way, you could solve the quadratic so you can just plug numbers in straight from here. Did you guys know that? You could actually solve your quadratic so you can plug these numbers in. And it would automatically solve for a quadratic of that. It takes a bit of work though, so unless you have to, I wouldn't recommend it. All right, does anybody have any questions about any of this? Okay, so you would get a concentration here. Remember though that whatever concentrations you get, you have this in with ammonia, right? So it's going to be reacting and binding with that ammonia. Remember that? Okay. And what does that mean? Well, that means that whatever concentration you get, you only have a fraction of that will actually be zinc 2+, right? So that's that fraction right there, 1.8 times 10 to the -5th. So you have to multiply those to get your free zinc 2+, okay? And then you take negative log, of course. C will then be after the equivalence point, which is the 60 mils. Remember that after the equivalence point, almost all the zinc is going to be binded, and so it will be in the form of zinc gamma 2 minus. Don't forget your dilution factor, which will be 50 out of 110. So we go ahead and calculate how much of this we have. 50 over 110. Again, that's that initial concentration of the EDTA and zinc in this case. We don't have to worry about which one's less. So this would then give us that number there. We know that the concentration of excess EDTA, because we're going to have just excess EDTA that will greatly overwhelm everything else, right? That will greatly overwhelm the unbound EDTA. So all we have to do is just take the 10 extra milliliters over 50 over the equivalence point, divided by 110 for the dilution factor, and then multiply by the initial concentration of the EDTA. And that gives us that. So once we know these, we can then plug these into our KF expression. Notice our KF expression at equilibrium, or at the equivalence point, excuse me, and at this point, 10 mils after the equivalence point, this term right here is different. Right? Because at the equivalence point, all your EDTA is used. You know, it's matching, right? You don't have any excess. After the equivalence point, you always have excess, which is why we have to calculate the excess here. Okay? Anybody have any questions about that? Because you have 10 milliliters of excess EDTA that was added that won't be used up for your calcium, right? Or, sorry, zinc 2+ in this case. Not that particularly matters, right? But zinc 2+. Because remember, you're 10 milliliters after the equivalence point at 60 mils, right? 50 mils was the equivalence point. 60 milliliters brought you to 10 milliliters after the equivalence point. Okay, so you plug these numbers in then. Remember that this will no longer be X down here, this EDTA, this will be a number. You are making an assumption, by the way. That assumption is that this minus X, this plus X don't matter because they're too small, which turns out to be a great assumption. Really smart assumption, right? That will always be a good assumption, by the way, for these problems. Because by definition, you had to have used up all your zinc 2+, right? So you have to have almost no zinc 2+ left. So that assumption will always be good. Okay? Yeah, you get that number and then you're good to go, right? Notice your math actually simplifies greatly after the equivalence point, because you don't have to solve for that x squared, right? Remember that was x squared before? Right there. Okay. So there's a variety of different metal ion indicators or endpoint detection methods for these. We have the metal ion indicators, which are the most common form of endpoint detection because they're a color change, they're easy to put in, they're easy to use, right? And they're cheap. Well, relatively cheap, at least for the initial setup costs. We have mercury electrodes, we have ion selective electrodes, and we have a glass pH electrode. So the metal ion indicators are going to be compounds that will change color when they bind to a metal ion. They must bind metals less strongly than does EDTA, because if they bind more strongly, they'll pull them from EDTA, right? And then we won't be indicating the end of titration, we'll be pulling it off the EDTA, not doing the titration, right? This is actually a surprising number of dyes, and you guys have used dyes that would work for these things, for like iron. Remember how we detected iron in organic chemistry by putting in, well, we didn't detect iron, we used iron to detect a product. So an example would be the reaction of magnesium 2+ with EDTA at pH 10. You can use the Kalmagite indicator, which is this right here. The magnesium with the indicator is a red color. The indicator alone is a blue color. So when you have not titrated it completely, it'll be reddish colored. When you have titrated it completely, it will be a blue color. In between, when you're getting to there, you'll have a purplish color because red plus blue is purple, right? Okay. These are some of the different ion indicators. Notice that most of these indicators will work for certain charges. So there's certain brackets of charge and size that they will work with. Most indicators don't work with just a single ion and are not that selective, okay? So like a lot of them that will work with calcium will also work with magnesium because they're not that different. All right? And you guys will actually experience that, not this lab, but next lab, the next experiment. These are what the indicators look like, by the way. These are the indicators. If you ever need to select an indicator, this is the information you'd use to do so. All right? Notice the pKa's here. Be very careful about those because some of them don't give you the same colors at different pH brackets, right? And so if you use these not understanding what you're supposed to see, you can really, really screw up, of course. Again, this is an indicator table. This is probably the most useful way of using an indicator table to figure out your indicator you need, okay? Let's say you're using EDTA for titration. You're probably going to want something in the pH 10 region. And so you'd want to go down pH 10, look for your metal ion, and find any indicators that change color around that region, right? Notice if you're forced to use something that's not pH 10, you need to use the fraction of EDTA will not be 0.3, right? If you were forced to use something down here at pH 6, your fraction of EDTA in the Y4 minus form would be much lower. So when you're actually doing calculations, you'd have to use that number, okay? Which is like 10 to the negative, what, 5 or 8 or something? It was very low, right? You guys remember the table that has the different amounts of EDTA that would be in the Y4 minus form? No? That's where we got the 0.3 from? No? Okay. Okay. Just know that if you're the 0.3 for the alpha for EDTA is how much of it is in the Y4 minus form, right? How much it is fully deprotonated. And so when we're using EDTA at a lower pH, less of it will be in the chelating form, the Y4 minus form, right? That has been tabularized for pH 25, or temperature 25 degrees Celsius at different pHs in a table in your book, okay? Which is where we got the 0.3 number from. That's the one for pH 10. If you use it at pH 9, that's a different number. If you use it at pH 8, that's a different number. Lower numbers. Okay? Go and look back. It's table 12.2, I believe. 12-2. All right. Anyways, if you do a good job selecting, you may be able to use it just a pH 10, and that's always the best because it gives you the most EDTA you can use. All right, so these are some of the different EDTA titration techniques. By the way, these ones will actually cover these more in later chapters. We have an electrochemistry chapter where we'll talk about these different electrodes. Okay. So you have two different major titration techniques. There's, of course, the direct titration, where your analyte will be titrated with your standard EDTA. The analyte is going to be buffered to a pH where K prime, remember K prime is that 0.3 times the KF, because we don't have all of it in the Y4 minus form. So you'll want to buffer the pH where K prime F for that metal EDTA complex is large, because you want EDTA to bind it very well, right? And you want to be able to use most of your EDTA. You don't want to have to put in 1,000 milliliters for every effective milliliter, right? Can you imagine how bad that titration would be? Can you? You need 1 microliter, use 50 milliliters to get it, because your pH is like 4. Yeah, wow, huh? Okay, so by the way, a common mistake. People do that all the time when they haven't been doing these very much. Again, you want that complex, metal EDTA complex KF to be large. The color of the free indicator is different from that of the metal indicator complex. This is why this chart's important, because you can see that you may not be there. Certain metal lines with certain indicators won't be there, right? They won't have color changes. So that'd be a problem. Again, that's what we're looking at. Okay. So those are two of the situations you need to understand. The back titration can also be used. Remember, the back titration is where you completely overwhelm one form, and then you would titrate backwards until the color changes. Okay? This is going to have a known excess of EDTA added to your analyte, and so the excess EDTA will then be titrated with a standardized solution of a second metal ion that would bind. And so then you use up all your EDTA, and it would have a color change when your free metal becomes large enough to see using the indicator, right? By the way, this is one of the methods you can use if your indicator is not giving you color, like you can't find one for your metal line here that gives you a good color change. What you do is you put too much EDTA and an excess EDTA, a known amount of excess EDTA, and then you back titrate using a metal line here that gives you a good color change with that indicator. Can you see that? Fantastic. All right, this isn't anything special for math or difficulty level really. So the nickel 2 plus can be analyzed by back titration using standard zinc 2 plus at pH 5.5, was xylenol orange indicator. A solution containing 25 milliliters of nickel 2 plus in dilute HCl is treated with this EDTA. The solution is neutralized with NaOH, and the pH is adjusted to 5.5 with acetate buffer. The solution will turn yellow, then you have a few drops of indicator added. Titration with this amount, so this concentration of zinc 2 plus, would require 17.61 milliliters to reach your red indicator endpoint. So what is the molarity of nickel 2 plus in the unknown? So what you're just going to do is you're going to use up your EDTA first with your zinc, right? And whatever EDTA is remaining, that's where you have to do your math. So your unknown was treated with 25 milliliters of this EDTA. You calculate the number of moles, or millimoles in this case, will be easier to work with, of EDTA. So you just multiply those numbers. That'll give you millimoles. Your back titration required this amount of zinc, 2+. So you take the milliliters times the molarity, that gives you millimoles. So the moles of zinc 2+ required in your second reaction plus the moles of nickel in the first reaction have to equal your moles of EDTA. Otherwise, they wouldn't give you an endpoint, right? So what we do is we set this up. The millimoles of zinc 2+ plus whatever millimoles of nickel, which we don't know, that's what we're trying to find, equals the millimoles of EDTA, right? That's straight up back titration calculation, right? Whatever remains, that's what we have, right? So we just do the math, we just subtract that off, we get 0.9159 millimoles of nickel. And because we have these all in milliliters, we can just divide that by the milliliters and we get the molarity. And that's it. Anybody have any questions? Okay, so displacement titrations, this is your third option. Ooh, okay. So remember, we have complexes that we can displace the metal ion in, right? So if we use a metal that binds better to EDTA than the metal that was there, what's going to happen? It's going to bind the EDTA instead, right? You all okay? You're looking at me like zombification happened. Okay, so you use this when the analyte, such as mercury 2+, does not have a satisfactory indicator. So something like mercury 2+, if you looked at that indicator table, it doesn't have a good indicator. It would be, you really don't have any way of doing that with a direct titration. So what we can do instead is we'll treat the mercury 2+ with excess magnesium binded to EDTA, or yeah. And that what's going to happen is the mercury is going to displace the magnesium 2+. So this is then going to be titrated with standard EDTA. So see, we're using magnesium in place to trigger our indicator, aren't we? So whatever amount here that the mercury will replace the magnesium, and we'll be left with an equal amount of magnesium now out in solution, right? So all we have to do is then titrate our magnesium 2+, and that will give us the amount of mercury that binds it. That makes sense? It's exactly what it says, isn't it? We're displacing another metal ion and then titrating that. Okay? So there's also no suitable indicator for silver. However, the silver will displace nickel from this chelating agent here, the tetracyanonickelate ion. So if we add the tetracyanonickelate ion, what will happen is 2 silvers will replace each nickel, and then we can titrate the nickel with EDTA using the nickel's indicator, and that will give us the amount of silver. Well, it'll give us half the amount of the silver. It'll give us a stoichiometric amount of the silver, right? Okay. Okay. We can also do an indirect titration. So anions that precipitate with certain metal ions can be analyzed with EDTA using an indirect titration. Here's an example of it, which is sulfate. Can be analyzed by precipitation with excess barium 2+ at pH 1. The barium sulfate is then washed when boiling with excess standard EDTA at pH 10. This will bring the barium 2+ back into solution as the barium EDTA. The excess EDTA is then back titrated with the magnesium. That back titration will then give us the amount of the barium, that had precipitated the sulfate, right? And once we have that barium, we have a stoichiometric amount of the sulfate. Does the stoichiometric amount sound okay to you guys? Do you understand what I'm talking about there? Like in this case, it's a 1-to-1 stoichiometric amount, right? Or normality, I guess, would be the correct way of saying that. But the more succinct way. The fifth way you can do these titrations is masking. So you'll take a masking agent, is going to be a reagent that reacts with a component of your analyte from reaction with EDTA. So literally you're going to mask one component from being able to react with the EDTA. Okay? An example of this is the Al3+ in your mixture of magnesium 2+ and Al3+. This can be measured by masking the shit, my example's messed up here. This probably was silver here, I guess. And you would need to mask one of the components so it doesn't react with your EDTA. I have this wrong right here. So what you would do is you'd react one with something that would not allow it to react with the EDTA, such as fluoride. So magnesium 2+ doesn't react enough with fluoride to cause it to precipitate or do anything special. So you don't have to worry about that. If you put that in with the aluminum, however, it's going to cause this to react enough that it will no longer show up for the EDTA. And essentially what you're using is you're using the difference in precipitations or the difference in complex binding for KFs, okay? So you're finding something that binds to one much better than the other and is strong enough binding it that the EDTA can't just pull it out. And the name pretty much explains it all, right? You're masking it so it doesn't show up. And those are your 5 methods. We'll go into the other types of ways of detecting these metal lines, the electrodes, later, okay? It's just